second lecture, and we are going to discuss problems on scattering parameters. The problem that I started in the last class, that is that of an ideal transformer, we had left with the question of whether S12 and S21 were equal and opposite of each other or not. Well, to calculate S21 we had terminated in 1 ohm, Vg1 terminate in 1 ohm, and this is V2. We have to calculate S21 by definition is twice V2 by Vg1 square root of, was it R1 by R2 or R1 by R2, and R1 and R2 are equal here, 1 ohm and 1 ohm, and therefore this factor goes to 1. All we have to calculate is V2, and for that we first calculate V1 that is this voltage, and since the impedance looking here is N squared, obviously V1, the equivalent circuit is this. In case you have not followed this, 1, what we see here is a resistance N squared, and this is V1. Therefore, V1 is equal to Vg1 times N squared divided by N squared plus 1. Okay. And V2 is, because the transformer is ideal, it is V1 divided by N. So, this is Vg1 multiplied by N divided by N squared plus 1. So, that S21, which is 2 V2 by Vg1, shall be given by S21 shall be given by twice N divided by N squared plus 1. Okay. Now, to calculate S12, what we have to do is terminate the primary in a 1 ohm, secondary the source, this is N is to 1 ideal, they should be the same, they turn out to be the same. This is Vg2 and this is V2. No, I beg your pardon, this is V1. Okay. So, all that you have to calculate is V2 here, and you notice that the impedance here is 1 by N squared. Therefore, V2 is equal to Vg2 1 by N squared divided by 1 by N squared plus 1, which is Vg2 divided by N squared plus 1. Okay. And V1 is N times this. So, N times Vg2 divided by N squared plus 1, which means that S12, which is twice V1 divided by Vg2, is equal to twice N divided by N squared plus 1, same as S21. Now, this should not surprise you, because the transformer, the ideal transformer, is a reciprocal device, and all we have done in calculating S12 and S21 is to interchange the source and the response, the cause and effect points, and the ratios should be the same. This is indeed so, from which we take the lesson that S21 must be equal to S12. This is the condition for reciprocity. Okay. Let us take another example in which the device is a distributed device. We have a transmission line. We have a transmission line of characteristic impedance Z0 and length L. Then in general, you know that if excited at x equal to 0, this is x equal to L, if excited at x equal to 0, then the voltage at any point on the line shall be of the form V of x equal to Vi e to the minus gamma x plus Vr e to the gamma x, where gamma is the propagation constant of the line, it is the square root of z y, where Z is the impedance per unit length and Y is the admittance per unit length. The characteristic impedance is square root of Z by Y. Okay. Now let's find the scattering parameters of this two port considered as a black box. Okay. These are the terminals, and let us say the terminating impedances both are Z0, the characteristic impedance. Then the reference impedances at both ports are Z0. All right. So if we want to calculate S11, we terminate this in Z0, all right, and find the impedance here. What is the impedance here? Z0, right? And therefore the reflection coefficient driven from a source of impedance Z0, reflection coefficient would be 0. There is no reflected wave, so S11 shall be equal to 0, and there is no reason why S22 shall not also be equal to 0. All right, for the same, under the same arguments. Is this point clear? That a transmission line terminated in its characteristic impedance produces an impedance equal to Z0 at its input. So the only thing that is to be calculated is S21 or S12. The two have to be equal because the transmission line itself is a reciprocal device, and therefore we need calculate only S21 or S12. Let us calculate S21, the forward transmission coefficient. For that we terminate the line in a source VG1 Z0, then this is the line.
So what if the termination was not by Z0?
Then it would be different. You would have a non-zero S11, non-zero S2.
The source would have also been different.
Yes, it could be different. We have taken the situation in which the terminations are equal and both are equal to Z0. If they are not, then there will be reflection coefficient at the input, there will be reflection coefficient at the output. Okay, let us say the green colored one is the line and this is terminated in Z0. What we have to calculate is V2. Okay, what we have to calculate is V2 and relate it to VG1. S21, if you recall, would be twice V2 by VG1. All right. Now also we also know that V of x in general is equal to Vi e to the power minus gamma x plus Vr e to the gamma x, but Vr would be equal to 0. Therefore this would be the general relationship. At any point x, this is x equal to 0 and this is x equal to L. At any point x, this would be the voltage. There is no reflected wave. All right, this has been made sure by terminating in Z0, both sides. Okay, so all that we have to find out now, okay, is this voltage. What is this voltage? This is Vi. How is it related to VG1? That is correct, because the input impedance is Z0 and therefore this is VG1 by 2, and this gives out Vi. What is Vi? VG1 by 2. Agree? Vi at x equal to 0, V of 0 should be equal to Vi is equal to VG1 by 2, and therefore the V2, the voltage at x equal to L, is simply Vg1 by 2 e to the minus gamma L. Okay, which means that S21 will be equal to simply e to the minus gamma L. There is a mistake in the textbook. This is the correct answer, e to the minus gamma L. The textbook says twice of this value, which is a mistake. Okay. Therefore, the scattering parameters of the transmission line terminated in characteristic impedance are 0, 0 diagonal elements, e to the minus gamma L, e to the minus gamma L. The equality of these two comes from reciprocity and anything else? Just reciprocity. No, symmetry does not guarantee, just reciprocity. Okay, so this is the scattering matrix. To denote that it's a matrix, I'll put a bar at the bottom. I'll underline the letter. Now let's take some examples from the example sheet. We take 14.1. 14.1 says determine the reflection coefficient S for the one port networks shown in the figure. The reference impedance is not given. Okay, reference impedance has to be given, otherwise you cannot find the reflection coefficient. So if it is not given, then you assume it to be 1 ohm. Alright, or you can assume anything. 1 ohm is a very nice figure, right? We are assuming 1 ohm because the element values that are given, well, 2 Henry, half farad, 1 Henry and so on. Suppose they are given in millis. I could have assumed a reference impedance is in a K, kilos and so on. Okay, all right. We shall work out the third problem, third network only. It says find the reflection coefficient S.
Excuse me, sir.
Yes.
So do we take it as 1 ohm for the second part as well, B part?
For all of them, for none of them it is given. Oh, for the B part, okay. For the B part you assume an R naught because the symbols, what is given is in terms of symbols. So you assume some value R naught, okay, and express in terms of R naught.
So we could might as well take these values as normalized impedances.
Which values?
All of these impedances, R1, R2.
As 1 ohm each?
No, so normalized.
As divided by R naught.
Okay, we could do that. We could do that. Then 1 ohm would be good enough. Okay. If the reference impedance is not given, it is your choice. If it is a 2 port and the terminations are given, then the choice is made. Alright, the choice is that the reference impedances are equal to the terminating impedance. Now, as I said, you have to find for the third network, the network is 1/4 ohm, 15 by 4 ohms and 16 by 15, 16 by 15 farad. So all that we have to do is to assume a reference impedance. We assume this is 1 ohm and find the input impedance. Scattering parameter S would be equal to Z minus 1 divided by Z plus 1. Let us look at Z. We have 1/4, 16 by 15 and 15 by 4. Z obviously is equal to 1/4 plus the parallel combination of resistance and capacitance, and I have already told you R divided by SCR plus 1. So 15 by 4 divided by S, 15 by 4 multiplied by 16 by 15 plus 1, which is equal to 4S plus 1. So it is 1/4 plus 15 by 4, 4S plus 1, which is equal to, I can take 1/4 common, right, 4S plus 1 and here 4S plus 16. That is correct. Therefore, I get Z as equal to S plus 4 divided by 4S plus 1. Agreed? Therefore, capital S is Z minus 1 by Z plus 1. So 4 minus 3S divided by Okay, 3 minus 3s divided by,
5s plus 5.
so 5s plus 5, which is equal to 3 by 5, 1 minus s divided by 1 plus s. Alright, similarly you can find out the other two networks. We shall skip 14.2, we go to 14.3. It says, for this network, for the network of problem 14.1, for the network, it should have been networks, there are 3 of them, determine capital S of j omega. Obviously, for this third network, 14.2, we are considering the third network. This is the value of capital S. So, magnitude S j omega, is it obvious that this is equal to 3/5?
Yes, sir.
1 minus j omega, 1 plus j omega, magnitude would be equal to 1. And you see that this is indeed bounded by upper bound unity. 3/5 is less than 4/5, correct? It is bounded, it is less than infinity, so it is bounded. Show that the scattering elements S for the networks in problem 14.1 are bounded real functions. Okay, you have to show that capital S is a bounded real function. This is not enough because this is on the j omega axis. You must understand this. Okay, a bounded real function is a function defined in the total S plane, not just on the j omega axis. So, in order to show that this function is bounded real, you have to write S of S as equal to 3/5, put small s equal to sigma plus j omega. Then you have 1 minus sigma minus j omega, alright, divided by 1 plus sigma plus j omega. So, magnitude S of S is equal to 3/5 square root of 1 minus sigma whole squared plus omega squared divided by 1 plus sigma whole squared plus omega squared. And if the real part, bounded real function definition contains the real part of S greater than or equal to 0. So, if sigma is greater than or equal to 0, then obviously magnitude of S of S is upper bounded by 3/5, and therefore S of S is a bounded real function. Is that quite okay? No, there is one step that we have skipped. You must bring in that step. What have we skipped? That capital S is real for S real. You must make this statement that by looking at this we see that if small s is real, then capital S is real, and therefore capital S is indeed a bounded real function. Consider 14.4, and we shall calculate for a couple of them, Let us take the second network, which looks simple. What you have to do is, for each of the networks shown, find the scattering matrix for a 2-port, given that the reference impedances at both ports are 1 ohm. R01 and R02 are both 1 ohm, and the network is this 1 1. I am not showing the dimensions. Then you have 2 and 2. This is the network. It is a 3-terminal network, and now to calculate S11, S22, S12 and S21, you will have to terminate. For example, for S11 you have to terminate this in 1 ohm and find the input impedance here. Let us say R in, it is resistive. Obviously S11 and S22 shall be equal. Is that correct? Because of the symmetry of the network. Because of the symmetry with respect to the ports, S11 and S22 shall be equal. You do not have to calculate again. but calculation of R input is cannot be done by inspection, because there is a bridging here. You have to write either KCL or KVL or use one of those transformations. Well, as I said, you don't have to commit to memory any formula, you can do it ab initio. You look at this as the parallel connection of this T, and the other network is a 2 ohm and a short circuit. So let's convert this T to a pi, and I shall do it ab initio without remembering any formula. Let's take this network 1, 1 and 2. Okay, this is port 1, port 2. Z11 is equal to 3 ohms is equal to Z22 because of symmetry. Z12 is equal to 2 ohms, this is equal to Z21. Therefore, the Z matrix is simply 3, 3, 2, 2, and the determinant of Z is equal to 9 minus 4, that is 5. What is the dimension? Dimensionless. Ohm squared. Isn't it right? Z22, Z11 minus Z12, Z21. Therefore, okay, Z matrix is 3, 2, 2, 3. The determinant Z is 5. Therefore, the Y matrix, which is the inverse of this, would be Z22 by determinant Z, so 3/5, then minus 2 by 5, and the rest is known, minus 2 by 5, 3/5. Therefore, Y11 plus Y12, we need this for the equivalent pi network, Y11 plus Y12, 1 by 5, this is equal to Y22 plus Y12, and Y12 is equal to, pardon me, minus 2 by 5. What I need is minus Y12, so it is 2 by 5.
Instead of doing this directly, we can add the Y parameters of the second.
Directly we can add
the Y parameters of the second circuit. That will be 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2.
We don't want to do that. You'll see that things are simpler than that. We don't. Our problem is not to find the Y parameters. Our problem is to find the equivalent network. Okay. So what we'll do is we shall draw the equivalent of this. Obviously, that would be, this resistance would be, no, 5 ohms. 1/5 is the admittance. This resistance would be 5 by 2, and this resistance would be 5. Okay. What did we have for the bridging? 2 ohms, and we terminated this in 1 ohm. All right. So the equivalent network is this. Now there is a reason why I don't want to add the Y parameters or simplify it further. Simplify it further only means that I shall combine these two and I shall combine these two. Let us see what does it become. 5, how much is this? 2 times 5 by 2 divided by 2 plus 5 by 2. This is equal to 5 multiplied by 2 divided by 9 equals to 10 by 9. Is that okay? 2 times 2.5 is 5 divided by 2 plus 2.5. That's correct. 10 by 9. And this resistance, how much is this? 5 by 6. Okay. So this impedance, this resistance therefore is 5 parallel the series combination of these two. How much is that? 10 by 9 plus 5 by 6. You know how I do things is I make this 18. So 15, 20, 35 by 18. Okay. 35 by 18, which means R in is equal to 5 multiplied by 35 by 18 divided by 5 plus 35 by 18. There is no reason why I cannot divide by 5. So 35 by, pardon me? 35 by 18. You guarantee this is 7 by 5? Okay, fine. So capital S11 would be 7 by 5 minus 1, 7 by 5 plus 1. This is equal to 2 divided by 12, which is 1/6. Alright? What is the dimension of S11? Okay, good. And this should also be equal to S22. Agreed? S22 is also equal to 1/6 because of symmetry. Okay. Now the problem of calculation of S21. Calculation of S21 is good enough because the network is reciprocal. Okay. So for S21, what I have to do is I have to connect a 1 ohm VG1, then this network 1 1. Now you will understand why I didn't do all that manipulation earlier. I have a bridge element of 2 ohms, I have a 2 ohms here, and then I have to terminate this in 1 ohm and find out V2. Okay. Now this network I have already simplified. So let's take that simplified form. VG1 1 ohm. Yes, what did I have? 5. Then here 10 by 9, and here does this change V2? No, you must see that it doesn't change. So this is V2. How do I solve this? Do I apply node equations or mesh equations? No. All I have to do is to find V2 by VG1. So I apply Thevenin to the left of this. Okay. What do I get? I get VG1 5 by 6. Open circuit voltage 5 ohms divided by 5 plus 1, 6. And what is the equivalent resistance of 5 ohms and 1 ohms? Yes? 5 by 6. Then I have 10 by 9, okay, and 5 by 6. This is V2. Therefore, V2 by VG1 5 by 6 is equal to 5 by 6 divided by this plus this plus this, which is 10 by 6 plus 10 by 9. Therefore, V2 by VG1 is equal to 5 by 6 into 5 by 6. 5 by 6 plus 5 by 6 is 10 by 6. Okay. So this would be 10. How much is this? 18.
The whole thing is half.
Whole thing is half. How did you do this so quickly?
So because 10 by 6 is 30 by 18, and that is 20 by 18, so that will be 50 by 18. Upstairs we have 25 by 36. So
You have calculated S21 directly?
Yes, S21 is half.
S21 is half, is it?
yes, sir.
Hold it. Oh, you're pretty smart. I can't do things so quickly. Yes, you're right. It agrees with my results. S21 is half. And this is also equal to S12. Okay? You understand that given a problem, given a simple problem, there is a simple solution. Okay? If you start writing mesh equations and node equations, you are going into a mess. Alright? And it may be difficult to come out of that. Fortunately, the numbers are not too nasty here, 1, 2 and 3, things like that. So, but what I am emphasizing is, given a problem, if you can solve it by inspection, do that. Because inspection is very difficult to make a mistake. You have to make a positive effort to make a mistake in solving a problem by inspection, if it is solvable. If it is soluble, for example, that bridge network, there is no way you can do it. You have to make a conversion. Either you have to make a conversion or you have to write the mesh equations or node equations. Okay. Let's take the third problem in 14.4. That is a negative impedance converter. That is, we have a two-port NIC in which V1 I1, V2 I2, and the NIC is defined by V1 equal to N V2, I1 equal to 1 by N I2. Can you tell me what is the difference between an NIC and an ideal transformer? What is the difference? There is a minus sign. In the ideal transformer, it's simply a minus sign. That's all. Okay. All right. Now let's see how to calculate the S parameters. For now, we cannot calculate one and say the other will be equal or opposite or whatever it is, isn't it? Because this NIC is not a reciprocal device. Okay? I didn't add necessarily. It is necessarily a non-reciprocal device. Isn't that right? You see, if the sign here was minus, then it was a reciprocal device. Since the sign is not minus, it is necessarily a non-reciprocal device, and therefore we cannot rely on calculation of one parameter to calculate the other. We have to do all the four. Now what we do is to calculate, well, R01 and R02 both are 1 ohm, so we terminate in 1 and find out the the impedance here, R1, which is equal to V1 by I1. V1 is NV2. This is the style of calculation. I don't go to anything else. I go to the fundamentals. Divided by I1 is 1 by N I2. So this is equal to N squared V2 by I2. Now you recall the signs. So this is minus N squared. And if that is so, then obviously S11 would be minus N squared minus 1 divided by minus N squared plus 1. Agreed? Z minus 1 divided by Z plus 1. That is equal to N squared plus 1 divided by N squared minus 1.
1 minus.
No? N squared, that's what I wrote. N squared minus 1. Okay. For S22 now, my termination will come on the other side. Please be careful. This is 1. This is V1 and this is I1. I have to calculate the impedance here. R2 is equal to V2 by I2, and the definition says V2 shall be V1 by N divided by I2 shall be N times I1. So this is 1 by N squared V1 by I1, and V1 by I1 is minus 1. So this is minus 1 over N squared. Therefore S22 is equal to minus 1 over N squared minus 1 divided by minus 1 over N squared plus 1, which is equal to, if I multiply by N squared, if I multiply by minus N squared, 1 plus N squared divided by 1 minus N squared. And you notice that this is exactly equal to minus S11. Alright? This is not true in general. In general, any non-reciprocal device, this is not correct. Okay? This is true only for this specific case of NIC. Now let's look at S21 and S12. We have the NIC. For S21, we have to connect a source VG1, 1 ohm, terminate in 1 ohm, and this is V2. Okay, how do I proceed now? I proceed in the same manner.
Minus I.
Pardon me?
So Vg1 minus I is equal
No, I don't go that way. There is a simpler way. All we have to calculate is V2. That's right, I calculate V1.
So we have
Minus n square. Minus n
by
square.
V1.
This is minus n square. We have already calculated this. And therefore V1 is equal to minus n square divided by minus n square plus 1. And V2 is equal to
So it
V1
will be
by-
V1. So V1 is equal to minus
multiplied by Vg1. Okay.
and V2 is n V1.
V2 is n times
No,
V1.
one by
V1 by
n.
n.
V1 by n.
Oh dear. Plus V1 by n. Agreed. That is equal to minus n
Minus n.
Vg1 divided by minus n square plus 1. Therefore S21 is equal to
Minus 2n by 1 minus n.
or 2n divided by n squared.
1
Minus.
minus n square. Oh yeah.
Okay, I have taken care of the negative sign. Alright, I have to calculate next, finally, I have to calculate S12, and for that one should not jump into conclusions. With non-reciprocal devices, one has to be absolutely careful. 1 ohm, and this is Vg2. The calculation procedure is the same. This impedance is, as we know, minus 1 over n squared. Therefore V2 is this voltage, is Vg2 minus 1 over n squared divided by minus 1 over n squared plus 1. And V1 is
n times v2.
n times V2. Therefore this is equal to Vg2 minus 1 over n minus 1 over n squared plus 1. Let's multiply by minus 1 over n minus n squared, then I get n divided by 1 minus n squared. Therefore S12 is equal to twice n divided by 1 minus n squared, which is exactly
S2.
minus S2. This shows the non-reciprocal nature of the device. Okay. Unfortunately, we cannot do 14.5 or the rest of the problems because we have not done it in the class. Let us conclude this class with the last example under 14.4, which is an extremely simple network, just a shunt element Z. Okay. Can one, it is a reciprocal network. It is also a symmetrical network. Therefore, calculation of S11 suffices. Can you tell me what this is? Well, the input impedance would be Z divided by 1 plus Z. No? If I terminate this in 1 ohm, then the input impedance is Z divided by 1 plus Z. So this minus 1 divided by Z divided by 1 plus Z plus 1. This would be my S11 or S22, which is equal to minus 1 divided by
1 plus 2z.
1 plus 2Z. Minus 1. Does it bother you? If it is 1 ohm, it is minus 1 divided by 2 plus 3. Okay. What about the S21? We have 1 ohm, Vg1, Z and 1 ohm. This is V2. So V2 is equal to Vg1 Z divided by 1 plus Z, equivalent of these two, divided by 1 plus Z divided by 1 plus Z. That is equal to Vg1 z divided by 1 plus 2z. Okay, therefore S21 is equal to 2z divided by 1 plus 2z. A couple of questions before we close this class. This is of course equal to S12 because the network is reciprocal. Okay. Is it possible to have a network in which the S parameters do not exist? You see, there are networks in which Z parameters do not exist, Y parameters do not exist. H parameters, do they always exist? ABCD parameters always exist. There is no network in which ABCD parameters do not. But what about H? Pardon me? There is no network in which H parameters do not exist. Is that correct? Double negative. Don't choose another. Then it becomes a problem. What about S parameters? Can you think of a network in which S parameters do not exist? If not, why not?
When resistance is equal to negative,
Resistance is negative, that is perfectly alright. The parameters
is equal to minus R naught.
But 0.
Say it again.
So the reference, the input impedance is negative of the reference.
Input impedance is the negative of the reference impedance. Just a minute. What you are saying is Z minus R0 divided by Z plus R0.
Z is equal to minus R0.
Okay. So it is possible.
It
That-
don't exist at that time.
Why not? Look, we have already had, this is why I asked the question, we already had an example in which the parameters may not have existed.
Yes, sir.
Yes? No. You see, look at this NIC example. S11 and S11 was n squared plus 1 divided by n squared minus 1. So when n is equal to 1, it doesn't exist. Similarly, you see S22 for that case should also not have existed. What about S12 and S21? Same. And therefore scattering parameters belong to the same category as Z or Y. They may or may not exist. They are conditional. Okay. But one thing is sure about scattering parameters, that the numerator of all the parameters is a reflected wave. Isn't that right? The numerator, either it is 1 1 or 2 2 or 1 2 or 2 1, the numerator is a B parameter and the denominator, can you tell me what is S21?
B2 by A1.
B2 by A1. So it is Sij, so it is Bi divided by Aj. Okay? Pardon me? S21 B2 by A1. Correct. Under the condition?
All other i's are 0.
All other AIs are 0, I not equal to J. Agreed. Now here all other i's not equal to 0, we are assuming a multiport, more than 2, which also shows that scattering parameter description is equally good for more than 2 ports. It could be a large number of ports, doesn't matter. But the point that I wanted you to notice is that numerator is a reflected parameter. Reflected parameter may or may not exist. Alright? May or may not exist. If it doesn't exist, it means that the reflected variable is 0. But what hurts it is if an Aj is 0. How can an Aj be 0? If the reference impedance is taken equal to the terminating resistance. You shouldn't forget so quickly. A2 equal to 0. What was the interpretation? R2 was equal to R02. So it was a choice. And therefore, right from this definition, without going into that example, you should have been able to say that scattering parameters may or may not exist. But if they exist at high frequencies, it is a boon. The description becomes very, very simple. We close at this point.